So in this last video, we're going to talk about how we can take all the techniques that we spoke of in the modules so far and put them together in order to demonstrate a technique for solving systems of linear equations using matrix vector form, which is known as Cramer's rule. And I'm sure that many of you have heard of this before, and you might wonder, well, why are we going over in the Intro to Engineering class? And to be honest with you, the main reason that we're going over with it is when we do the lab, which will be due next week, what you'll find is that by kind of coding up how to do Cramer's rule in MATLAB, it allows me to introduce you to concepts of software engineering without necessarily feeling like we're jumping right into coding. So if you think about those 2x2 systems of equations that we looked at in a previous learning module, you probably know that there's different ways that you can go about solving those. You can graph both equations, as we mentioned beforehand. The set of solutions lie along a line, and you can look for the point of intersection. Or you can use algebraic techniques like substitution or elimination. However, we're going to, and I mentioned that you can kind of look at these in this week's lab in that bullet. I'm probably going to take that out, although I will actually encourage you to, if you want to work them by hand and kind of refresh some of the old techniques, to feel free. But really what I'm going to ask you to do is to solve a 2x2 system of equations using Cramer's rule, both by hand and by MATLAB. So what is Cramer's rule? Well, for now, let's just focus on the fact that it's going to require us to compute what is known as a determinant of a 2x2 matrix. So what I'm showing you here, if you notice I just have three things equal to each other, that's showing you that there's lots of different ways to write a determinant. You can take the matrix that you're going to take the determinant of and write the letters DET outside and put it in parentheses. You can use a delta, which is nothing more than this Greek letter that looks like a triangle, and put parentheses again and put the matrix inside. Alternatively, the way I'll usually do it is put the matrix inside not of square brackets, but of absolute value brackets. However you write it, the way you compute the determinant is the same thing. You take the elements on the downward diagonal, A and D, you multiply them together, and you take the elements on the upward diagonal, B and C, you multiply them together, and then you take the difference. So it's a product of the downward diagonal, A times D, minus the product of the upward diagonal, B times C. And remember, you might say, oh, why isn't it C times B? It's really just a matter of how you write it, since matrix multiplication, of course, commutes. So how do we actually use this to solve for the two unknowns in the 2x2 system of equations, which are x and y? Well, here's how we're going to do it. We're going to say that x is equal to the ratio of two determinants, just like y. Now, notice in this formula that the denominator of both the solution for x and y is the same. It's nothing more than the determinant of A, remember, is just the coefficient matrix. So if the coefficient matrix has elements A, B, C, D, its determinant is just going to be A times D minus B times C. So I'm not showing you the actual formula there because you have the formula of how to compute the determinant on the prior slide. Now, where people get confused is what the determinant of the matrix in the numerator is for both x and y. So you notice I'm calling this A sub x. That's oftentimes called an augmented matrix. And the way that I'm going to change matrix A, you might assume it's some change on the matrix A since it has the same big letter but just a different subscript. Since I'm solving for the first unknown, I'm going to take the first column of the matrix A, and I'm going to swap in the constant vector. So no longer will I have A and C in this first column, I'll have K1 and K2, but the second column stays the same. For the unknown Y, since it's the second unknown, I'll swap in that constant vector into the second column instead. First column stays the same, second changes. So it looks like it's a really complicated formula, but remember, for both the numerator and denominator here, you're just going to compute a determinant, which means multiply on the downward diagonal minus multiply on the upward diagonal. So you'll get some practice on this in this week's lab in MATLAB, but we're also going to look at an example right now. So say you had a 2x2 system of linear equations, 1x plus 1y equals 5, minus 1x plus 2y equals minus 2. How could you actually go about solving that using Cramer's rule? And again, I'll upload these solutions in case you want to go back and look at them. But the first thing you need to do is actually put it in matrix vector form. So since these two equations are already in standard form, for my coefficient matrix, the first row will take on the coefficients of the first equation. I'm going to choose to order it x first, y second, since that's how they're written. So in row 1, column 1, I'll have the coefficient of x in equation 1, which is 1. In column 2, the coefficient of y in equation 1, which is 1 as well. Second row will be the coefficients minus 1. Don't forget, whenever you don't see it, if there's nothing there, it's a 1. If there's a minus there, it's a minus 1. Coefficient of y is 2. Since I chose to structure them x first and y second, my unknown vector gets an x on top, y on the bottom, and then the constant vector on the right side takes on the constant of the first equation, which is 5, and then in the second row, it's minus 2. So how do I actually define the matrices that I need to take the determinants of? Well, remember that A is just the coefficient matrix. It's the matrix that you have here on the left already. So 1, 1, minus 1, 2. How do I take a determinant? I multiply down the downward diagonal. I multiply up the upward diagonal, and I subtract the two results. So 1 times 2 is just going to be 2. Minus 1 times 1 is minus 1. Don't forget, when you subtract a negative, minus minus becomes plus. So determinant of A is actually 3. How do you determine the determinant of AX? Well, how do you actually set up AX? Remember, it's the first unknown, so I'm going to augment the coefficient matrix by taking the first column, swapping it out, and putting in the constant column. So 5 minus 2 becomes the first column. Second column stays the same, 1, 2. Take a determinant, downward diagonal product, 5 times 2 is 10. Upward diagonal product is minus 2. 10 minus a minus 2 is 12. How do I form the augmented matrix Y? Well, it's the second unknown, so leave the first column alone. And for the second column, swap in the constant vector. And you notice that's what I've done here. You kind of see the pattern now. Compute the determinant, you get 3. Now, how do you actually find the two unknowns, X and Y? Well, remember back to the formula from the module. X is nothing more than the ratio of the determinant of AX to the determinant of A. That's just 12 divided by 3, which is 4. In a similar fashion, y is the determinant of AY divided by the determinant of A. 3 divided by 3 is just 1. So the solution to this system of equations is x equals 4, y equals 1, which we can write as an ordered pair. And if I were to substitute those back in to either of these two equations, note that 4 plus 1 is 5, and that minus 4 plus 2 times 1 is 2, minus 4 plus 2 is minus 2. So hopefully that makes sense to everyone, and hopefully you enjoyed this lecture, kind of an intro to engineering math. Again, the main actual point here, even though linear algebra is incredibly commonplace across all the domains of engineering, whether it's applying numerical methods in simulations to solve partial differential equations, as I think I gave you the example of antenna design, but it also holds if you're trying to optimize the geometry of a car or wind in order to make sure that you minimize wind drag and make it energy efficient. Under the hood, this is what's going on. Not in 2x2 systems, of course, very, very large systems. In a similar fashion, if you're dealing with artificial intelligence, that underlying mathematics is all linear algebra. So really, really important stuff to know. But for us, it's going to be a vehicle through the lab this week to get a handle and intro into programming.